Okay, the third speaker of this session is Shengyi, who is going to tell us about bidirectional higher rank polymorphism with intersection and union types.
Okay, so is everything working in the audio? Okay. Hello, everyone. I'm Shengyi. Today I'm glad to talk about bidirectional higher rank polymorphism with intersection and union types. This is joint work with Chen and my professor Bruno Oliveira. So this talk will be divided into 4 parts. The first is a general introduction to the background, and secondly, our system, we call it FEIU. And third part is how to formalize this system, its correctness in the work prover, and the last part is the conclusion and summary. So let's first go into the background to introduce some notions and concepts that may not be very familiar to the audience. The first thing I would come up with is the higher rank polymorphism. I think maybe it's the most unfamiliar concept. So it can be viewed as a generalization of the parametric polymorphism existing in the Hindley-Miller style type system. Where in Hindley-Miller type style system, you're only allowed to write this kind of polymorphic types where the quantifiers appear in the top level. So you cannot represent a function that takes a polymorphic function as an input. That generalization somewhat mitigates this problem, but it's still not general enough. So you want this for quantifiers to really appear in arbitrary types. So we have this notion of high rank polymorphism that allows the 4 quantifiers to appear inside function types. And the rank n polymorphic type is the function type that with a rank n minus 1 type as argument. And here are some examples of rank 1 and rank 2 types, and you can make arbitrary rank types just by nesting them inside. And the second notion is intersection union type. Because these things usually have a very clear theoretic interpretation, so it's usually most people have a very clear intuition about it. So a term has an intersection type means it has both types. A term has union types means it has either types. And these subtyping rules characterize this theoretic notion. In more complex systems with intersection union types, you sometimes have more complex subtyping rules like distributivity, but we don't consider them here. And these 2 sets of features were studied independently by various of works, but their interaction or combination was rarely studied. But we think it's an interesting problem for various reasons. First, they are both core features of several mainstream languages like Scala and TypeScript. In TypeScript, you use these intersection union features to represent heterogeneous list, mixing patterns, overloading, and various other patterns in dynamic languages. In Scala, intersection union types also appear in the dot calculus. And I don't have to mention the necessity of parametric polymorphism here, I guess. And secondly, in recent studies, people find that their combination is expressive enough to type a large portion of dynamic language. You don't need gradual typing, but you already use these features. You give static types to a large portion of programs. A second, parametric polymorphism and intersection types are both important mechanisms to represent polymorphism. One is closed word, one is open word. And the last thing is the explicit type application. It complements the above 2 features very well because it allows programmers to provide complex and ambiguous instantiations. Like for a lot of systems, you cannot do full inference. You really want the programmers to provide some help to the type inference engine. And also, these features are also supported by most languages because in a lot of languages, you don't even have this inference, so you need the programmers to provide them anyway. And for this complex type system to work, we must have some sort of type inference. And type inference itself is an ambiguous notion because people mean different things. Here, we are not so ambitious to mean that Hindley-Miller type style inference that you infer all types from no notation. We are in general interested in 2 cases. The first is implicit instantiation, which again, in general consists of 2 cases. You want to apply a polymorphic function to a specific argument, and you want an argument with a more general type to be regarded as an argument with a more specific type. So in both cases, we want these instantiations to be automatically inferred by the type inference engine. The second rule may be a little bit weird. The second case may be a little bit less sane because it requires the idea of polymorphic subtyping. It says a polymorphic type is a subtype of another as long as you can find a proper instantiation. So we use a different symbol tau here because in a lot of cases, this instantiation is not a full type set. We only want a subset of the type to be automatically inferred. We have this quite widely used dichotomy, which is first is predictive instantiation, that the instantiation itself only consists of monomorphic types. The second is they allow to contain arbitrary types where the instantiation themselves can be polymorphic. For example, in this case, we instantiate this A with this for all A to A, so the ID function can be applied to itself. We are also interested in some sense of inferring simple functions without annotation. So when a function has a monomorphic type, we also want to avoid the annotation burden. So we use a bidirectional framework to do this. The bidirectional framework in general consists of two modes: the inference mode or the synthesis mode, where this type A is the output. You only examine the expression, and you won't get the type. And you also have this checking mode. You both have this E and A as input, and you want your algorithm to check. So the inference and checking alternate between each other. You get the result of the whole algorithm. Next, we will go into our system. So we have this philosophy that's infer easy, or in our sense, it's practicative instantiation. But we allow programmers to provide all the impractical instantiations so that we don't lose any expressivity. It can be viewed as an extension of previous work by our group to support first-class intersection and union types. So actually, in a later stage of our research, we find that our system is quite similar to how actually the algorithm in TypeScript works. They seem to, based on our observation, we don't really have the proof because we don't really check its code, but based on its behavior, we think TypeScript seems to be loosely based on Dunfield and Krishnamurami's ICFP 2013's work with certain ad hoc design choices to support intersection and union types, as well as has more other features in TypeScript. But since our study is a formalized study, so our system provides a more disciplined treatment, and it has the following advantages. It supports all the relevant quantifier, and thus we have the checking subsumption properties for the type system. We also support more complete overloading, and we have less syntactic restriction on writing polymorphic types. We also support intersection introduction rule and the monomorphic function inference, as we mentioned before. We also have the guaranteed monotype instantiation, which is a corollary of the completeness of our algorithm. So most of these concepts are self-explanatory, and we have more examples and text in our paper. But one thing that may be not that self-explanatory may be the first one. So in general, it is known that all the irrelevant quantifier is incompatible with explicit type application, because with explicit type application, the instantiation is bound with a certain quantifier. So it doesn't make any sense if you swap the order, and these things should still work. But it turns out that TypeScript, because we guess it's based on decay, it still takes this approach. Okay. So it loses the property of checking subsumption. That means if your program's type checks, you want to replace the type with a super type, the type checking should still succeed, but in this case, it fails. Okay, you don't have to lose that. You don't have to look at the concrete example, but it's basically what the idea is basically what I mentioned here. So let's look at the rules of the system. This was original rules of the elementary type inference. We have unit type, the type variable, the subtype variable, which we will introduce later, the for all type, the function type, and also top and bottom type. And you also have this type abstraction and type application. So as we mentioned before, since we have type application, we want all the relevant quantifier that rejects this kind of subtyping, where these two types only differ in the order of the quantifier, but we don't want the subtyping to hold between them. And also, it has a restriction on the polymorphic type. It only allows full real polymorphic type, that you don't allow this for a int, which is basically the same as int. So to achieve the first one, we need to modify the subtyping rules. This is the for L rule we mentioned before. This is the for R rule. So it says we can extract the type variable on the right-hand side to the context, and this variable may be used by this tau later, by later invocation of this for L rule. So instead, we change this rule to only compare two for all types. And also, we introduce this subtype variable, which is not a monotype, so it will not be used by later instantiations of for L rule. We also add a restriction in the for L rule to say we always prioritize this rule over this rule when both sides are for all types. The syntactic restriction is easier to implement. We just add more conditions in the well-formedness check to ensure the formation of types and expressions. With the introduction of intersection types, things actually become trickier. because in the subtyping of intersection and union types, you sometimes discard one branch. So it makes some checks useless because sometimes you perform a check before and this branch is just called discarded. So in this case, for the intersection type, we need this type variable to appear on both sides to make no counterexample happen. For union types, things are still usual. You only need this type variable to be mentioned by one branch. So it means this type is well-formed, and this type is not. So this is a subtyping rule. The new things are marked blue. So the black things, I think they are rather standard, like bottom types, type variables, function types, and the for all rules and for all rules mentioned before. The subtyping rules of intersection and union types are also standard. The only thing left here is what syntax restriction should we put here? If we put the old thing, the thing doesn't work, we have an intransitive subtyping relation. It's basically because you can have a type which is not a for type syntactically, but it's equivalent to a for type. It's just you can use intersection union types to bypass this syntactic check, and you result in an intransitive subtyping relation. So the simplest thing to avoid this is that we put a very strict restriction to say that we don't invoke a for L rule when B is a for type, intersection type, or union type. It works, but it's too restrictive. It rejects too many things. Even though for rules will not be invoked later, we still too eagerly decompose the right-hand side. So what we want is a similar asymmetric syntactic restriction, just as the free variable check before. And when we have this syntax check in the for L rule, we still have good subtyping, and we have more expressive subtyping. So this subtyping now holds. And you can find the implicit instantiation to be int. This is the typing rule. So the typing rules is in the bidirectional style, and we add these three rules for the checking rules of intersection and union types. This is a intersection introduction rule, and we still need this because we have a restricted inference ability, so sometimes we still want to relay the type information to the inner expression. And we also have these two auxiliary judgment here. It's basically can be viewed as constrained inference, which you want to make sure the inferred type has a specific shape. So it has, in this case, it should be of a function type. In this case, it should be either for or bottom type. So it can be applied or type applied. And we can have a glimpse on our algorithm presented in the worklist formulation that we have this automatic scope management. And we also turn our guessing of instantiations into constraint solving and generation. This is one case of generation, and this is two cases of solving. And we also use continuation passing style to delay some information that we don't know, but we need to create the judgment here. So when we infer the type of E, we will make it a subtyping judgment and to perform later check. So let's slightly have a quick look at the formalization. So one big difference is that previous works in this line of work usually use Arbella. Arbella has built-in support for bindings, so it's very easy to use in that sense. But we turn to Rock, so we also need to use a new infrastructure based on locally nameless style, and we use Alt and L engine to achieve this. And this is a proof structure that with properties proved in each system, and the arrows indicate their relative soundness and completeness. Here, soundness and completeness means whether they infer the same set of programs and type check the same set of programs. We also have introduced this intermediate worklist to bridge the gap between these two systems, so it makes the whole proof simpler. So these are the properties formally speaking. So we have subtyping transitivity, we have checking subsumption, and we also have type soundness by elaboration to a type sound system, which is a system F with record and product. With product and sound, sorry. And we also have the soundness and completeness of our algorithm. Basically, it says what our specification states, our algorithm will succeed. And what our algorithm succeed, it also follows the specification. And our algorithm is also decidable. Here we state this in a more specific version where expressions are closed on the empty context. But actually, when we prove them, we need to generalize to the open context and worklist. And since we move to locally nameless style, actually it motivates us to rethink a lot of decision choices made before about the formalization. One thing we mentioned here is a transfer relation to relate the algorithmic worklist and the intermediate worklist. So here we need to define this transfer relation to interpret, because this thing only exist in the algorithmic worklist. So we need to interpret this thing as a word form declarative type. And previously, this was a transformation used before. You can see it examines the worklist from beginning to the end, which contradicts to the usual inductive structure of a list. And it also has substitution everywhere. And it really complicates things a lot. And instead, we develop a syntax directly transfer that makes things much simpler. So basically, the general idea is we kept track of explicit substitution set to track all the instantiation, and we don't do the substitution eagerly. So this is the rules. They are quite structural, so we can just skip over them quickly. And also, we have other design choices. Basically, we have a defunctionalized version to represent the continuation parsing. So everything can be inductively defined in Cork without further proof burden. So let's go to the conclusion. So this is a summary of the contribution of our system. We have a bidirectional system for high-rank polymorphism with intersection and union types, and it has good properties. We also had a sound, complete, and decidable algorithm for this system. We then started 2 extensions in our paper. The first one support record, and the second one both support record and a relaxed monotype definition. So all the things are formalized in Cork, and we also provide a prototype implementation in Haskell. Thank you, everyone. And questions are welcome.
OK, we have time for some questions.
You mentioned something about deriving monotypes when they exist. So something, could you clarify? Is it like if there exists a monotype instantiation, you're guaranteed to find it by your inference algorithm? Or
no. It's just we don't need this as a premise to make sure. It's just if our algorithm finds one, it means there exists one by the specification. And if the specification guesses one, it means our algorithm can find that.
OK, so it sounds. You said if
and
there
if
exists,
there
then
is
you can
no,
also find
if the specification cannot find one, well, it means this program will not be type checked by our specification, so it should be rejected. So our algorithm will also report an error in this case.
OK.
Yeah.
And then I had another question. The slide had something about more expressive overloading. Could you clarify sort of more expressive compared to what? Or is it just because you allow for high-rank polymorphism, now you can have overloading, which is also high-rank types? One of the first slides with the contributions or...
I think it has similar expressive power to TypeScript. You basically, based on in Flow, you actually have more complete, let's say, constraint solving, because TypeScript, based on DK, they use a similar solving strategy as we do. But Flow and maybe Scala 3, they gather more constraints and you solve them laterally. So you can have, in certain cases, better solving solutions. But we do have very similar expressive power with TypeScript, let alone other features in TypeScript. Yeah.
OK, we can take it offline. Thanks.
OK, let's thank you again. Thanks.